Hello and most welcome to 1538, and we will continue with the connection between time and mathematics that we started last lecture 1537 with Nicolas Gisin, the Swiss mathematician who objects to the idea that the law of the excluded middle should rule what we think about the world. So he's questioning that. A true revolution, I would say, and a most important job. I will expand the ideas a little bit by going into an article from Quantum magazine written by Dave White. So if we can get some more sun here. Yeah, it's a nice sunny day. It's a little bit chilly to be May. It could be like 14-13 degrees, something like that. But we are slowly getting there. Summer temperatures. Does time really flow? New clues come from a century-old approach to math. The laws of physics imply that the passage of time is an illusion. To avoid this conclusion, we might have to rethink the reality of infinitely precise numbers. If numbers cannot have infinite strings of digits, then the future can never be perfectly preordained. Introduction. Strangely, although we feel as if we sweep through time on the knife edge between the fixed past and the open future, that edge, the present, appears nowhere in the existing laws of physics. In Albert Einstein's theory of relativity, for example, time is woven together with the three dimensions of space, forming a bendy four-dimensional space-time continuum, a block universe encompassing the entire past, present, and future. Einstein's equation portray everything in the block universe as decided from the beginning. The initial conditions of the cosmos determine what comes later. And surprises do not occur. They only seem to. Listen to this quote. For us believing physicists, Einstein wrote in 1955, weeks before his death, the distinction between past, present and future is only a stubbornly persistent illusion. The timeless, predetermined view of reality held by Einstein remains popular today. The majority of physicists believe in the block universe view because it is predicted by general relativity, said Marina Cortés, a cosmologist at the University of Lisbon. However, she said, if somebody is called on to reflect a bit more deeply about what the block universe means, they start to question and waver on the implications. Physicists who think carefully about time point to troubles posed by quantum mechanics, the laws describing the probabilistic behavior of particles. At the quantum scale, irreversible changes occur that distinguish the past from the future. A particle maintains simultaneous quantum states until you measure it, at which point the particle adopts one of the states. Mysteriously, individual measurement outcomes are random and unpredictable. Even as particle behavior collectively follows statistical patterns, this apparent inconsistency between the nature of time in quantum mechanics and the way it functions in relativity has created uncertainty and confusion. Over the past year, the Swiss physicist Nicolas Gisin, as a mathematician, as a physicist / mathematician, has published 4 papers that attempt to dispel the fog surrounding time in physics. As Gisin sees it, the problem all along has been mathematical. Gisin argues that time in general and the time we call the present are easily expressed in a century-old mathematical language called intuitionist mathematics, which rejects the existence of numbers with infinitely many digits. When intuitionist math is used to describe the evolution of physical systems, it makes clear, according to Gisin, that time really passes and new information is created. Moreover, this formalism, the strict determinism implied by Einstein's equations, gives way to a quantum-like unpredictability. If numbers are finite and limited in their precision, then nature itself is inherently imprecise and thus unpredictable. physicists are still digesting Gisin's work. It's not so often that someone tries to reformulate the laws of physics in a new mathematical language. But many of those who have engaged with his argument think they could potentially bridge the conceptual divide between the determinism of general relativity and the inherent randomness at quantum scale. I found it intriguing, said Nicole Younger-Halpern, a quantum information scientist at Harvard University, responding to Gisin's recent article in Nature Physics. I'm open to giving intuitionist mathematics a shot. Cortege called Gisin's approach extremely interesting and shocking and provocative in its implications. It's really a very interesting formalism that is addressing this problem of finite precision in nature, she said. Gisin said, it's very important to formulate laws of physics that cast the future as open and the present as very real, because that's what we experience. I am a physicist who has my feet on the ground, he said. Time passes. We all know it. That's a nice bit of confidence. Information and time, next subtitle. Gisin 67 is primarily an experimenter. He runs a lab at the University of Geneva that has performed groundbreaking experiments in quantum communication and quantum cryptography. But he is also the rare crossover physicist who is known for important theoretical insights, especially ones involving quantum chance and non-locality. On Sunday mornings, in lieu of church, Gisin makes a habit of sitting quietly in his chair at home with a mug of oolong tea and contemplating deep conceptual puzzles. It was on a Sunday about 2.5 years ago that he realized that the deterministic picture of time in Einstein's theory and the rest of classical physics implicitly assumes the existence of infinite information. Consider the weather. Because it's chaotic and highly sensitive to small differences, we cannot predict exactly what the weather will be a week from now. But because it's a classical system, textbooks tells us that we could, in principle, predict the weather a week on, if we only could measure every cloud, gust of wind, and butterfly's wing precisely enough. It is our own fault we cannot gauge conditions with enough decimal digits of detail to extrapolate forward and make perfectly accurate forecasts, because the actual physics of weather unfolds like clockwork. It's getting warmer here too. Now expand this idea to the entire universe. In a predetermined world in which time only seems to unfold, exactly what will happen for all time actually had to be set from the start. With the initial state of every single particle encoded with infinitely many digits of precision. Otherwise, there would be a time in the far future when the clockwork universe itself would break down. But information is physical. Modern research shows it requires energy and occupies space. Any volume of space is known to have a finite amount of information. Finite information capacity, with the densest possible information storage happening inside black holes. The universe's initial conditions would, Gisin realized, require far too much information crammed into too little space. A real number with infinite digits can't be physically relevant, he said. The block universe, which implicitly assumes the existence of infinite information, must fall apart. He sought a new way of describing time in physics that did not presume infinitely precise knowledge of the initial conditions. The logic of time, next subtitle. the modern acceptance that there exists a continuum of real numbers, most with infinitely many digits after the decimal point, carries little trace of the vitriolic debate over the question in the first decades of the 20th century. David Hilbert, the great German mathematician, espoused the now standard view that real numbers exist and can be manipulated as completed entities. Opposed to this notion were mathematical intuitionists led by the acclaimed Dutch topologist L.E.J. Brouwer, who saw mathematics as a construct. Brouwer insisted that numbers must be constructible, their digits calculated or chosen or randomly determined, one at a time. Numbers are finite, said Brouwer, and they're also processes. They can become even more exact as more digits reveal themselves in what he called a choice sequence, a function for producing values with greater and greater precision. By grounding mathematics in what can be constructed, intuitionism has far-reaching consequences for the practice of math and for determining which statements can be deemed true. The most radical departure from standard math is that the law of excluded middle, a vaunted principle since the time of Aristotle, doesn't hold. The law of excluded middle says that either a proposition is true or its negation is true. A clear set of alternatives that offers a powerful mode of inference. But in Brouwer's framework, statements about numbers might be neither true nor false at a given time, since the number's exact value has not yet revealed itself. Oof. There is no difference from standard math when it comes to numbers, like 4, a half, or pi. The ratio of a circle's circumference to its diameter. Even though pi is irrational, with no finite decimal expansion, there's an algorithm for generating its decimal expansion. Making pi just as determinate as a number like half. But consider another number, x, that's in the ballpark of half. Say the value of x is 0.4999, where further digits unfurl in a choice sequence. Maybe the sequence of 9s will continue forever, in which the case converges to exactly a half. But if at some future point the sequence a digit other than 9 crops up, if say the value of x becomes 4.99999 and so on until the very end, and then we have a 7. Then no matter what happens after that, x is less than a half. But before that happens, when all we know is 0.4999. We don't know whether or not a digit other than 9 will ever show up, explained Carl Posey, a philosopher of mathematics at the Hebrew University of Jerusalem and a leading expert on intuitionist math. At the time we consider this x, we cannot say that x is less than a half, nor can we say that x equals a half. The proposition x is equal to a half is not true, and neither is its negation. The law of the excluded middle doesn't hold. Moreover, the continuum cannot be cleanly divided into two parts consisting of all numbers less than a half and all those greater than or equal to a half. If you try to cut the continuum in half, this number x is going to stick to the knife, and it won't be on the left or on the right, said Posey. The continuum is viscous. It is sticky. The unfolding of time. Hilbert compared the removal of the law of the excluded middle from math to prohibiting the boxer the use of his fists. Very good. I like his quote. Since the principle underlies much mathematical deduction, although Brouwer's intuitionist framework compelled and fascinated the likes of Kurt Gödel and Hermann Weyl, standard math with its real numbers dominates because of ease of use. The unfolding of time, next subtitle. Gisin first encountered intuitionist math at a meeting last May, attended by Posey. When the two got talking, Gisin quickly saw a connection between the unspooling decimal digits of numbers in this mathematical framework and the physical notion of time in the universe. Materializing digits seem to naturally correspond to the sequence of movements defining the present, when the certain future becomes concrete reality. The lack of the law of the excluded middle is akin to indeterministic propositions about the future. In a work published last December in Physical Review, Gisin and his collaborator Flavio del Santo used intuitionist math to formulate an alternative version of classical mechanics, one that makes the same predictions as the standard equations, but casts events as indeterministic, creating a picture of a universe where the unexpected happens and time unfolds. It's a bit like the weather. Recall that we can't precisely forecast the weather because we do not know the initial conditions of every atom on Earth to the infinite precision. But in Gisin's indeterministic version of the story, those exact numbers never existed. Intuitionist math captures this. The digits that specify the weather state ever more precisely and dictate its evolution ever further into the future are chosen in real time as that future unfolds in a choice sequence. Renato Renner, a quantum physicist at the Swiss Federal Institute of Technology, Zurich, said Gisin's argument point in the direction that deterministic predictions are fundamentally impossible in general. In other words, the world is indeterministic. The future is open. Gisin said, is not unfolding like a movie in a cinema. It is really a creative unfolding. The new digits really get created as time passes. And I think we make a little conclusion there. So you can so far see what this most interestingly is pointing to. And it's odd that all this is quite recent. We're talking about just a few years ago, and things that never ever been questioned, so to speak. Yes, of course, intuitionist maths been around almost, well, a century, that is. But now this is coming up within physics. It makes it so much more interesting and pertinent. And I think it's hard to overvalue what this can produce. As I said in the earlier lecture 1537, we all live in a deterministic world. That's the default mode of understanding anything today. And that means it will be incredibly important, all the developments and understandings that we do. They have great actual effects on our understanding of the universe, and it makes perfect sense even to an amateur as me that of course information takes space. Of course it's not non-spatial somehow, situated in some transcendental Neverland. It is here. It is in this world information is stored, wherever it is. And all of a sudden, the defining conditions of the deterministic world doesn't make any sense anymore. It started from a false thinking from the beginning and has been ever since false. Non-consistent, non-coherent with what is sound and wise. Put a little pause there, and I'm going to put something on the whiteboard. So we check that. So the point is, there simply is not enough space in the universe for storing information about these initial conditions. We know that information takes space, but nowhere does it has any possibility of being stored. And Nicolas Gisin, of course, put great emphasis to this understanding. It's of utmost importance. It changes everything. We have been living in a sort of dream world where we've been thinking that information doesn't take space, it's sort of non-spatial. In a way, it's sorry about the hat. In a way, it's a variety of the age-old idea of res extensa and res cogitans. Unquestioned and unthought of. We need to think these things clearly, and the discovery, if you may, by Nicolas, Gisin and Poussy opens an unknown door to a better understanding of these things, a more real one. You can imagine having the conception that more knowledge can be stored than actually can. It's like imagining planets, whole solar systems with no proper extension, or galaxies just popping up from nowhere, not making any. But since we didn't know knowledge-wise about these things, they enter smoothly and easy into the relations, and thereby will take a decisive role within thinking and correcting it. Once we understand information is spatial, without the sufficient space, information will be more and more limited, but it's always finite. No one ever has proven the ideas of David Hilbert and many others that information is infinite, or where that information would be present. Until such a time someone is pointing to that fantastic place of infinite information, we need to get down to what is possible and not what is impossible. And how also this indirectly has rid us of our own time. We no longer understand time. Time we will discuss in earlier in the lectures. We talked about before and after the ordinal numbers, and that's another factor of great importance that should not be, so to speak, ignored, because it takes great knowledge reduction to ignore ordinality, what is first, what is second. I mentioned earlier, even in the body, that is the most important division. And it's, of course, as the last quote here, I had some more. I'll begin with the strongest one by Renato Renner, a quantum physicist at the Swiss Federal Institute of Technology, Zurich. And he said that Gisin's argument, quote, point in the direction that deterministic predictions are fundamentally impossible in general. In other words, the world is indeterministic, the future is open. Time, Gisin said, is not unfolding like a movie in the cinema. It is really a creative unfolding. The new digits really get created as time passes. The other quote I do here, or reference, is with a very good example of x, and how we cannot say that x is less or 5 until we do the calculation. And the idea that it is either false or correct is most definitely wrong. It doesn't take either value. And of course in this you can also see a connection to the quantum superposition, where it is most definitely not settled before anything has been observed. You can compare that to do the mathematics or think them through. Until that very moment, nothing is set. It is completely open to either existing or non-existing. It is deeply unsettled. It is more to do with what is easy to use, and standard math with its real numbers are incredibly easy to use. They do invite to clearer, easier math, and the whole world is today deeply accustomed to this way of doing things, and therefore it persists. It doesn't seem to disappear easily. It cannot. It's too well established. It's too much of tradition, a habit, and I would say the rather sharp remark by David Hilbert that taking away the law of the excluded middle from the mathematicians is equal to forbidding the boxers to use the use of their fists. Excuse me, just gonna So here you can see the traffic light, the semaphore once more. I think it's very useful to understand what is the law of the excluded middle and its deep connection to time. Can you see the connection? Is it understandable that with a regular classical time, in a way, the law of the excluded middle is a sort of a necessity, something that is very hard to get away from. And you can compare that to Poussin's and Gisin's, Nicolas Gisin of Geneva, Renato Renner of Zurich, and Posse of Jerusalem University. This viscous now and dense future. Viscous now meaning if you try to cut it to get out a now, the knife will stick midway. And in this article, you understand this on the foundation of half. That half doesn't become truly half until you've done all the calculation. That might never happen, and therefore the knife sticks in between what is closer to 1 and what is closer to 0. Hereby fixating, making the stroke of the knife, the sharp samurai sword, if you like, impossible, invalid, hopelessly so. And we never know, and I think this is very good by Carl-Posey. We never know if another digit than 9 will ever show up. So in this infinite take on mathematics, where nothing really ever stops, we get this gigantic problem of the knife not being able to cut anything, and instead it gets stuck. No escape, not getting anywhere. And this is very close to the weather. I think the weather example here is absolutely brilliant. Recall that we cannot precisely forecast the weather because we don't know the initial conditions of every atom on Earth to infinite precision. But in Gisin's indeterministic version of the story, those exact numbers never existed. Intuitionist math captures this. The digits that specify the weather state ever more precisely and dictate its evolution ever further into the future are chosen in real time as that future unfolds in a choice sequence. That points to a very important feature in this open-ended take on the universe. Heidegger, quantum gravity. I continue on page 5 here after where I ended with Gisin. Heidegger, a quantum gravity theorist at Imperial College London, said she is very sympathetic to Gisin's argument, as he is, quote, is on the side of those of us who think that physics does not accord with our experience and therefore it's missing something. Heidegger agrees that mathematical languages shape our understanding of time in physics, and that the standard Hilbertian mathematics that treats real numbers as completed entities is certainly static. It has this character of being timeless, and that definitely is a limitation to us as physicists. If we're trying to incorporate something that's as dynamic as our experience of the passage of time, for physicists such as Heidegger, who are interested in the connections between gravity and quantum mechanics, one of the most important implications of this new view of time is how it begins to bridge what have long been thought of as two mutually incompatible views of the world. One of the implications it has for me, said Renner, is that classical mechanics is in some ways closer to quantum mechanics than we thought. Quantum uncertainty and time. If physicists are going to solve the mystery of time, they have to grapple not just with the space-time continuum of Einstein, but also with the knowledge that the universe is fundamentally quantum, ruled by chance and uncertainty. Quantum theory paints a very different picture of time than Einstein's theory. Our two big theories on physics, quantum theory and general relativity, make different statements, said Renner. He and several other physicists said this inconsistency underlies the struggle to find a quantum theory of gravity, a description of the quantum origin of space-time, and to understand why the Big Bang happened. If I look at where we have paradoxes and what problems we have, in the end always boil down to this notion of time. Time in quantum mechanics is rigid, not bandy and intertwined with the dimensions of space, as in relativity. Furthermore, measurements of quantum systems make time in quantum mechanics irreversible. Good point here. Whereas otherwise, the theory is completely reversible, said Renner. So time plays a role in this thing that we still do not really understand. Many physicists interpret quantum physics as telling us that the universe is indeterministic. For Christ's sakes, this weird word, it's a quote. You have two uranium atoms, one of them decays after 500 years, and the other one decays after 1,000 years. And yet, they are completely identical in every way, said Nima Arkani Hamid, a physicist at the Institute for Advanced Study in Princeton University, Princeton, New Jersey. In every meaningful sense, the universe is not deterministic. And this is getting even more interesting. What a bona fide. Still other popular interpretations of quantum mechanics, including the many worlds interpretation, manage to keep the classical deterministic notion of time. alive. These theories cast quantum events as playing out a predetermined reality. Many worlds, for instance, says each quantum measurement splits the world into multiple branches that realize every possible outcome, all of which were set in advance. Gisin's ideas go the other way. Instead of trying to make quantum mechanics a deterministic theory, he hopes to provide a common indeterministic language for both classical and quantum physics. But the approach departs from standard quantum mechanics in an important way. In quantum mechanics, information can be shuffled or scrambled, but never created or destroyed. Yet, if the digits of numbers defining the state of the universe grow over time, as Gisin proposes, then new information is coming into being. Gisin said he absolutely rejects the notion that information is preserved in nature, largely because there is clearly new information that is created during a measurement process. He added, "I am saying that we need another way of looking at these entire ideas." This new way of thinking about information may suggest a resolution to the black hole information paradox. Which asks, what happens to information swallowed by black holes? General relativity implies that information gets destroyed. Quantum theory says it's preserved. Hence the paradox. If a different formulation of quantum mechanics in terms of intuitionists' math allows information to be created by quantum measurements, perhaps it also lets information be destroyed. Jonathan Oppenheim, a theoretical physicist at University College London, believes information is indeed lost in black holes. He doesn't know if Brewer's intuitionism will be the key to showing this, as Gisin contends, but he says there is reason to think information creation and destruction might be deeply related to time. Information is destroyed as you go forward in time. It is not destroyed as you move through space. The dimensions that make up Einstein's block universe are very different from one another. And that's an important thing that gets ignored in the so-called normal take. Time is nothing like space, and space is nothing like time. Although in the Einsteinian take it gets all the same. But time and space are incredibly different. Information to disappear as time makes, that's just incredible compared to space, which preserves information. Time is a different animal altogether. Along with supporting the idea of creative and possibly destructive time, intuitionists' math also offers a novel interpretation of our conscious experience of time. Recall that in this framework, the continuum is sticky, impossible to cut in two. Gisin associates this stickiness with our sense that the present is thick, a substantive moment, and listen now, rather than a zero width point that cleanly cleaves past from future. In standard physics based on standard math, time is a continuous parameter that can take any value on the number line. However, Gisin said, if the continuum is represented by intuitionistic mathematics, then time cannot be cut in two sharply. It's thick in the same sense as honey is thick. And of course, poor old Zeno, his paradox here flies away forever. So far, it is just an analogy. Oppenheim said he had a good feeling about this notion that the present is thick I am not sure why we have that feeling. And I have to say, as a commentator, I completely agree. There is a thickness to the now. Now is a thing to be considered. It's not a no thing. The future of time. Gisin's ideas have prompted a range of responses from other theorists, all with their own thought experiments and intuitions about time to go on. Several experts agree that real numbers do not seem to be physically real, and that physicists need a new formalism that doesn't rely on them. Ahmed al-Mahiri, a theoretical physicist at the Institute for Advanced Study, who studies black holes and quantum gravity, said quantum mechanics precludes the existence of the continuum. Quantum math bundles energy and other quantities into packets, which are more like whole numbers rather than a continuum. And infinite numbers get truncated inside black holes. A black hole may seem to have a continuously infinite number of internal states, but these get cut off, he said, due to quantum gravitational effects. Real numbers cannot exist because you can not hide them inside black holes. Otherwise, they'd be able to hide an infinite amount of information. And once more, we have this irresolvable problem with infinite information that real numbers could bring. They do not even fit. Not even one real number fit within a black hole. And I think we discovered the largest black hole ever recently, a couple of weeks ago. Not even that one would be able to host a single real number. Sandu Popescu, a physicist at the University of Bristol, who corresponds often with Gisin, agreed with the latter's indeterministic worldview, but said he is not convinced that intuitionists' math is necessary. Popescu objects to the idea that digits of real numbers count as information. Arkani Hamed found Gisin's use of intuitionist math interesting and potentially relevant to cases such as black holes and the Big Bang, where gravity and quantum mechanics come into apparent conflict. These questions of numbers as finite, or fundamentally things that exist, or whether there's infinitely many digits, or the digits are made as you go on, he said, might be related to how we should ultimately think about cosmology in situations where we do not know how to apply quantum mechanics. He too sees the need for a new mathematical language that could liberate physicists from the infinite precision and allow them to talk about things that are a little bit fussy all the time. Gisin's idea resonates in many corners, but still need to be fleshed out. Going forward, he hopes to find a way of reformulating relativity and quantum mechanics in terms of finite, fuzzy intuitionists' mathematics, as he did with classical mechanics, potentially bringing theories closer. He has some ideas about how to approach the quantum side. I think it's about time for a sort of a recollection here. I think this is quite revolutionizing. It's incredible that it took such a long time until it got revealed, so to speak. But this, of course, changes everything. It will be the death of Tegmarki and Manuel's interpretation. And those are theories solely, I need to write that down. The sole reason for Manuel's interpretation is determinism. Without determinism, it will disappear directly. It doesn't have any point at all. It will be like a snowball in hell. It will be gone before it even enters. Because the bifurcations, not in a good way here, but the bifurcations that determinism make are absolute. There is no disappearing of information, and therefore for every bifurcation there is a new world created. So we have this black hole of Platonist mathematics somewhere, and thanks to that black hole of not knowing, there is a huge amount of things that sort of flower from that, or germinate from that. I think that's the best expression. And one of those things is a determinate world with set initial conditions. God throws dice only one time in this conception, the Tegmarkian, Hugh-Everetian conception. And once he's done that, every time there is a happening, because Tegmark doesn't really understand or realize time either. For every moment, there would be a divider that makes a new world, makes a new world, makes a new world. Because everything was determined from the beginning, and there's no time in many worlds theory, not at all. It shares with the classical physics, greater part of quantum mechanics today. It's an interesting, incredibly revealing, underlying mathematical substratum. And for my part, I think it's very interesting. We happen to take these aspects to the fore. We brought Brewer up, and also Bishop, who was, so to speak, a successor of Brewer in the United States. And I even contacted a modern day constructivist mathematician. Oh, I forgot, he had a very odd name. But it's hugely interesting. I had no idea what's happened now, more or less. It's only a couple of years into the past. This is a grand moment. It comes close, actually, in some ways, to the Nobel Prize for the 3 quantum physicists. It's absolutely up there in the highest forms. And of course, the thickness of the now is, in this model, many worlds of the classical physics, psychology, anthropology, all subjects. It's something subjective, nothing to do with the world as such. So that actually deprive people of time. They lose time. They lose time, not like hours, weeks, years. They lose it in an even more fundamental sense. They lose contact with time. No longer knowing what it is, not being able to relate to it anymore. It's like it never existed anywhere. And you be living outside of the time for the rest of your life. And I always felt that the idea that time is another dimension, a 4th dimension in general and special relativity, doesn't make any sense at all. He's extrapolating a 4th dimension from the 3 ones already so to say, made earlier on. And then he makes a 4th one and he calls it time. Fits, but many things do fit. It goes against all intuitions that time would be a spatial dimension. Is it a dimension at all? You might remember Susie Froebel, Mark Starlov have been looking into fractal time and how absolutely different concepts we find there. That time is deep and wide. That it has the character as just described here of thickness and having the capacity to destroy information and of course produce information spontaneously like this. It's a vivid time. And of course that's the time of a living human being. Determinism rids us of everything. And it's one of those 2 or 3 things that it's so pushing in establishing a point from nowhere, as depicted by Thomas Nagel, and the universalist approach as Paul Feyerabend took up, who's been a tendency that has been so detrimental to the development of science in the last half century, if not longer, where physics has been dogmatized by unknown principles. Maybe the most fascinating is that it is completely unknown, unheard of, ununderstood, newly discovered by Nicolas Gisin in Geneva. And I can just imagine opening up this door to new understanding can bring so many new things about. A new understanding entirely directed into a reality of time is 100% real. And of course, it will also lead to a conception of space that is not from nowhere, where there isn't a demiurge at the beginning that throws dices and creates the whole world, and then it's absolutely set in stone what's going to happen. It's just horrendous. It's really horrendous. It's a cage. And I remember now, come to speak of it, when many years ago my first contact on a study level with quantum mechanics I took at the University of Gothenburg many years ago, 96, 97. I was asked together with another student to make a small lecture. We all were asked as part of the curriculum. And I come to the conclusion that it could be possible that quantum mechanics could make free will possible. And afterwards some people came out. We had like a break out in the fresh air up there in that lovely area of Gothenburg with old houses from the early 20th century, late 19th century. Richard just said, it's an excellent lecture you made, you and Maria. But of course there's no chance of free will. We all know that, and he included me in that proposition. I wasn't happy with it, but what could I say? I didn't have any defense for free will at all. Otherwise, a hope for free will in connection with quantum mechanics. But now it is blatantly clear that free will exist, since time doesn't repeat itself in that ludicrous way that we inherited, but were never able to sort of point to or go into question. It's not really what you do, just realize it's there. That was very interesting. Thank you for your patience, and have a very pleasant afternoon. Bye bye for now.